Let me check that my stream is actually working, because last time I was recording a whole stream about embeddings, and then it turned out that actually there was nothing showing. Hopefully this will not be check that my stream is actually working. Hopefully this will not be the case this time. Yeah, this is another stream on machine learning system design, the next part. I have streamed embeddings information yesterday. I wasn't sharing my screen because of a glitch, not because I was stupid this time. So I will call this part 2, the current stream, because the previous part 2 I have actually removed, so that no one can see this frustration. But maybe some other time I will re-record the embeddings video. If you want me to re-record it, feel free to ping me in some way. But otherwise, I will just continue speaking about other topics. And the today's topic is high cardinality features. So let me share my screen, and let's dive into that. What does it mean for us? Okay, so I will be sharing window this time. And I'm interested, will slideshow work? Or actually, let me also change the layout. So let me check if slideshow works at all. Give me a second. I'm checking on my iPad. I just need to see how the whole thing works. Okay, yes, it works. Wonderful. Nice. Let's see. We are discussing high cardinality features. So what's a high cardinality feature? I have shown you an example of a JSON that an ad exchange might send to different like bidders for, let's say there is a user and this user came to our site, and now we can show this user some ad, and those the exchange, like different bidders will compete for showing their ad at this particular place. So they will be paying different amount of money, and we will be choosing which one of them should we be showing here. How do we do that? And essentially, someone like Google solves this problem under the hood, and someone like Facebook, anyone who has ads, they're solving this problem by being like the only one, the only entity who can choose an ad to place in a specific place on a site, and they have all those ads, and they need to choose which one to show to obviously maximize their revenue, but also to achieve many other goals, like for example that people should be clicking on those ads, and they should be liking what they're clicking on, and there should be good long-term effects that we don't have users don't have ads fatigue, as it's called, that like as time goes on, they click less and less, or we increase churn because we are pushing some ads too much. So this is a hard problem, but today we will be focusing on a specific aspect of this hard problem, which is high cardinality features. So how are we getting these high cardinality features? Let's look at this JSON, and I have already highlighted high cardinality fields for you. So for example, if we have a specific site, right, where we want to place our ad, this will be a feature in our model, and there can be like millions of sites where or app, or any other surface where we are showing an ad. There can be millions of options. And what do? Do you want hot encode the whole million? So you have a million features just from that. And then there are zip codes, and like zip code combined with the city. Okay, maybe there are like hundreds, thousands of cities of interest that we can store. Zip codes, the same thing. There are probably like tens of thousands of zip codes, but maybe we just need to store some specific, like very small amount of these features. So, for example, let's just store top 10 cities, but that means that we are ignoring quite a lot of information that we could have been using in our information. Maybe there is a specific city where people like specific ads, but you get it. You cannot just ignore the information. It's always better to use the information that you have, but you just need to build the system in such way that under all the constraints, under latency constraint, under the inference cost constraint, you can still use this information and use it fast enough to show the relevant ad to someone. But yeah, also we have like different models of devices. And finally, we obviously have different users. So if we have like 2 billion users, do we also encode all of those users as a long vector? Obviously not. So you can tell me that already, right? We all know about embeddings, but what happened before embeddings and how this whole industry changed and where it came to now, this we will be discussing today. Okay, so now let's talk about the first thing. Before the 2010, we still needed to show ads somehow, and Google already monetized. I don't remember if Facebook was already monetizing, but sooner or later they will. And what is the approach that you can use if you want to, if you have a high cardinality features with million of possible values, like for example, as we have had previously, places where sites where we can advertise, or even like a billion or hundreds of millions, if we have users, we can use a hashing trick. So hashing trick is a very simple idea where we reuse the same bucket for different possible values for the cardinality feature. So let's say we use a hashing trick for our zip code, then the feature name will be zip code, and the zip code will be feature value, zip code itself. And then we just create a string out of this, and then we encode it, and then we hash it and create a specific integer. And here we have some number of buckets, and we use this, like we can create a specific length of the vector, and then each of our values will be placed in one of the buckets. So the problem there, right? Okay, let's talk about some things here. So first of all, it's extremely fast. So this whole calculation is very fast, and you have just constant memory. So you have a specific length of this vector with buckets, and you don't need to worry about this. And it also handles new ideas automatically. So let's say you one-hot encode something, and then if you just have a limited amount of columns, then what if you have a new value? You will have something like other, then how many other values will you have? That's a separate problem. But here you put everything in a specific bucket, even the values that you have never seen so far. Then uh, another issue is, or another benefit is that it actually works very well with linear models. So if you have a lot of data, you can create your bucket arrays to be quite big, and you will strike the right balance between the memory that you need and the information that you use in a specific model. And this will be kind of like one-hot encoding, but a faster solution. It works very well with logistic regression, and that's why logistic regression was a king for a long time, because you can easily train it online. It's very cheap for inference. You can create many complex features, like feature interactions, for when you need to combine signals from several features. Let's say the user has iPhone and also the user is between like 20 and 25 years old. Bam, that's a specific thing that we want to consider separately from everything else. But by just using hashing trick, I was talking about logistic regression. That's where we can combine, like multiply to one hot encoded vectors theoretically, and have user who has like 25 person who has an iPhone as a feature. But that is a feature interaction. And by default, this hashing tree doesn't have feature interactions. You are not encoding whether the person is from city, like from New York, and also that they are using an iPhone. No, you don't know that. The model will treat those probabilities separately. So let's say you're trying to predict the probability of a click and you're using logistic regression. Then both of those values will have a parameter and they will be kind of like independently affecting your probability. But in reality, you might assume that if the person is from New York, that's one thing. If they have an iPhone, that's a different thing. But if the person is from New York and has an iPhone, those features can be not just additive but multiplicative. So the basically combination of those two should have a different weight than those two, like a sum of those two features, if you get what I mean in terms of logistic regression. So sum of the weights for those two features and the weight for a combination of the features will not be the same thing. So these are feature interactions. We don't have those with hash and trick. How do we go about this? Well, factorization machines, here they come. So it was a great paper in 2010 by Randall, and he introduced factorization machines, but not only that, he also introduced a way to calculate things very fast in production. So how do we go about factorization machines? We not only create our buckets. Remember, right? Like we still probably need a hashing tree because we cannot encode all the zip codes. Maybe we need tens of thousands of um, one hot encoding for tens of thousands of columns if you want to encode all zip codes. So we probably are still using our factorization, our hashing trick. But then once we put a feature in the bucket, how can we find what are the feature interactions? Because for some feature interactions, the problem is that we have never seen those. There might have never been a combination of specific zip code and specific other parameter, and if that's the case, you don't have it in the training data. So all of the whole column with the multiplication of these two features will be a zero. How can you go around this fact? You can create vectors, embeddings actually, for each of those features. So when you're calculating an interaction between two features, you do a dot product of these two vectors, embedding vectors, and then you multiply the result by these two features. Why is this cool? It's cool because then when you see something in production for the first time, you can still multiply the vectors of those two features, even if they have never been multiplied during training, and you will get a reasonably good result. That's one part of the factorization machines. Another part is that even though you have like square kind of square complexity here, right? You can use a trick, a specific mathematical trick, and you can figure this out for yourselves that that's actually correct. And that's what another thing that Randall introduced, why this was used by everyone. If you just want to multiply all the features and you have like 1,000 combinations of features, right? So you have two vectors or like vector with itself that we project with hashing trick something on the vector of the length 1,000. Then we need to do cross features between all of the buckets in this hashing trick array, and then it will be 1,000 by 1,000, so it's now again a million. That's a problem, right? That will take a long time to calculate unless you use this idea that changes the ordering of the operations, and instead of O of n squared calculation, you get O of nk operation. And k is the length of our embeddings. And if k is relatively small, then you're saving enormous amount of compute by using this. So then it's very cheap to calculate cross features, and you can be happy about this. Okay, So now let's move on. What are the benefits? What are the problems of factorization machines? So the benefit is there is no manual engineering. So you don't have to try all the different combinations of features and see which ones are actually worth keeping and spend your data scientist time on that. And works, as we mentioned, when features never appear together in the training. But the problem is obviously again that we have only second order interactions. So we can do a cross of two features. So the user is from New York and has a phone, but not something like the user is from New York, has a phone, and is 30 years old. That you already can do. And it might still be worth it because again, the effect of combination of features might not be the same as like a sum of those weights. If you're using logistic regression, you can also use something more sophisticated. But yeah, maybe another important thing here to mention is that um, logistic regression works well with hashing tree, but something like gradient boosting trees doesn't work well. So yeah, probably whichever system you're building, you need to be uh, to choose the right balance between like whether you want to use a hashing trick for some high cardinality feature, or you, for example, want to one hot encode the top, I don't know, 100 values, let's say for cities, and then have other as another column for everything else. And remember, we still don't have embeddings yet as part of this whole computation. So yes, right now you probably will use something like embeddings, but we will get to that. We are not getting to that yet. Back to my point is that hashing trick works well with logistic regression, doesn't work well with trees. So if your model is tree based, then you probably shouldn't be using hashing trick and should instead use some more standard approaches. But still, factorization machines work either with hashing trick or with normal approaches. Um, so yeah, that's something to consider. Now, another approach that we can have, right? What we are trying to do is we are trying to figure out second order and like higher order interactions. But maybe some of those interactions are important and some are not. So the idea is here we don't have any interactions. That's sad. Here we have all second order interactions and we can calculate those relatively fast. That's great. But what if some of those calculations are actually wasteful? We don't want to do that. Then another option is what actually Facebook used a lot is you use gradient boosting decision trees and you feed them on your data. And then for any incoming data point, you apply this decision tree, gradient boosted decision tree, and you use the leaf ID as a one hot encoded feature. So you can create a relatively deep tree, and obviously the tree will segment your data in the best possible, the most informative way, so that when you get to the leaf stage, you will have a lot of information with non-linear border between different segments about like what does this specific leaf encode. So then you can use this as a one hot encoded vector, or like yeah, probably you won't be using hashing trick because here you don't have such huge cardinality, and it would partly defeat the idea. But you can use this as an ID and you can just pass it together with some other more dense features to your linear regression. It works well. So why does it work well? It's extensively non-linear, so we are memorizing just the right patterns, and we can also tweak how deep do we want our tree to be and many different things. So it's um, very beneficial to do it like this. And it's great at memorization, so we can find specific buckets that are especially useful to know about with this tree. But as I said, trees don't work well with hash and trick, so we need something called target encodings. So target encodings is another trick that we can use for high cardinality features if we are also using trees. But it's a mess. It's very hard to implement without messing up the like validation and testing and everything. So how are you doing that? You have a target. Let's say the target is like, I don't know, house price, or um, uh, it's a probability, it's a click rate. Like, does the person click or not? So basically, click through rate for a specific category. So what you can do is you can find the average value for this average target value for this specific bucket. So for example, what is the average CTR for New York? And use that as your feature. But once we do that, we start leaking. So we basically cannot, we need to calculate this always on the data that we are not using for training. So we cannot, if we use that to get our CTR, and then we are trying to predict on the same, like using the targeted encodings that we use to encode the target that we are trying to predict, then is leakage. And then we need to create some like methods like leave one out, target encoding, calculated by the bucket, and then use this value for the other buckets, stuff like that. So it's a mess and hard to reason about. That's one problem. Another problem is a two-stage pipeline that is also not end-to-end differentiable. So you have first a gradient boosting decision tree, and then you also have linear regression or neural network for that matter on top of it. So you would prefer this to be like differentiable end to end, but the problem is that um, you cannot use this final loss function that is used for output of your linear regression or neural network and put it back um, and propagate the error back to the level of your tree. So you just propagate it to the level of features, and then the tree works independently. So that's another problem of this approach. And then what else can we do? Here comes wide and deep approach. As you can see, Google has created this in 2016. One of the problems that I have seen, one of the errors I have seen people make is that they thought that wide part of of this model is when we apply gradient boosting decision tree, let's say, to the wide part, and then deep neural network to the other part, and then combine the results. No, that's not the case. That is what mostly what we were talking about just now. Here, wide part is just kind of like a logistic regression, but applied for as we were applying logistic regression before, right? That has many of those cross features, but mostly it's like uh, hand handmade logistic regression. So it's like one layer perceptron. Think about it this way. But then we also have deep layer for which might even have we don't use any like cross features, and we just put everything together, and then we start propagating this information through some relatively deep network, and then we combine the results. So let me just highlight what I was talking about right now. So you see wide layer is just a linear layer, and then we have, let's assume here we also have deep layer. Why is important? Sorry. Here we have a deep neural network. Why is this important? Because finally, for high cardinality features, we can start just propagating all the information back to the level of our ID, and then we can create embeddings for our users this way, which is cool. Now we can have embeddings for all our high cardinality features, and then it's much more information dense and useful. That's great. So getting back to what I was talking, right? So we have some high cardinality features for those we are using embeddings. Then we also have some dense features here, like dense X. So for dense features, we are using just like this deep layer. So sequential of layers, yeah, so linear. So deep input dimension. So we just concatenate our we concatenate our categorical features, our dense features, pass them through the deep layer. Then separately we apply wide layer. And then in the end, we just combine those wide logits and deep logits, and then return the logits. So that's why it's wide and deep. Why it's wide, let me again highlight. In the wide part, we do cross features. So even if we have like 1,000 features, maybe we are using hash trick, maybe we are using other approaches, we have 1,000 items. Then we are also using crosses for the features. So maybe those are manual, and then we have like 10,000 features or something, or 100,000 features for this part. But for the deep part, we have different features. Like we are essentially encoding them as embeddings instead, and like passing them through the network. Okay, so what's good, what's bad about this wide and deep approach? Here we are for the first time considering separately two problems that we have. One is memorization and another is generalization. So we are kind of incorporating inductive bias in our model. What does it mean? So memorization memorizes some specific combination of things that should be very informative for us, right? So again, like Apple user from New York, maybe I'm just speculating, but maybe this is very informative for what kind of ads we should be showing to this person. So we memorize that. But then we also want to have deep interactions, because then we can also use a lot of kind of behavioral aspects, like how user behaves on the platform, how many clicks have they done, what is their intent right now when they are visiting our site, what is the context where we are showing them the ad, right? All of that we can incorporate in this deep network. And then even if we haven't memorized anything about this specific user, we might still come up with a good recommendation. And then we combine those two things and we do a great, we achieve a great result. But the problem is that we still need manual crosses, and the interaction between features, this learning is still inefficient. So we still have to, for wide layer, we still have to manually create those crosses. We still need to figure out which crosses to use. So do you remember what was the solution for this problem before, when we needed to manually create a lot of crosses? Yes, it was factorization machines. So here come 1 year passes, deep factorization machines. So it's kind of, as you can see, right, between these pictures, it's pretty much the same thing. The only thing that changes is that here now we have factorization machine. And then here we are applying this to wide input. So previously we manually created crosses. Now we are using factorization machine to create these crosses. So again, what are the pluses and pros and cons of this? So finally, we don't need any manual feature crosses, but still limited to the second order interactions. The same issue for the wide layer as we had before with factorization machines themselves. And there finally was a solution. 2017, I think it was Google, but I'm not 100% sure, who introduced deep cross network. So let's look for some time at this particular thing. So what is happening here? We have our features, and we have several layers where we will be passing features through those layers. And just to be clear, this cross part is exactly about what previously was achieved with like factorization machines or just a wide layer in wide and deep. So the deep part of this wide and deep architecture is fine. It works. It works great. We are fine with that. But the cross network still has issues, and we want to address those. So how do we address those? We create this kind of like high cardinality feature solution, where we are multiplying our vector by a matrix. So as you can imagine, this thing, when you multiply vector by a matrix, it will result in some number. So here we have layer L. So we have our features that went through a set of layers, and they still stay the same width, so the same array size. here, and we multiply it by weights. So it's kind of like this part will be, oh, I can use the pointer, right? So this part, it will be kind of a logistic regression, right? Not logistic regression, but the regression itself, the simplest part. Then we will get some number, like there will be a scalar as a result, and we will modify this number by this scalar, and then we will also add these layer features by themselves, and then also some bias of this layer, and we will get the next layer. So we will be applying layer by layer, trying to learn those WL weights. And as you can imagine, there is an obvious problem that this just results in a scalar. Maybe instead we want to do a pointwise multiplication. So then instead of getting scalar, we need to get a vector of the same size. So this is a square matrix that we multiply by this vector. We get another vector of the same size. We add bias, and then we do pointwise multiplication. We add this vector back, and we get xl plus 1. So this is the next layer. Both architectures are pretty similar, so you can see it's just version 2 that addresses this specific scalar issue. So we're definitely doing more computation this way, but we also are getting more benefit because we are getting much more precise values and more precise behavior on each layer. So why do we need all this? Let's think about it for a second, right? So what do we get when we get for, let's say we do calculation for the zero layer, right? So all of those, it will be x1 and it will be x0 and it will be x0. So we use this matrix from zeroth layer, multiply those things. This is the result that we are getting, right? So now we do pointwise multiplication by our x, y, and z. Let's say x, y, z is like x0. And what do we get? We get essentially our cross features for the first layer, right? So we have some basic x, y, z, but we also get x squared, xy, xz, xy, y squared, yz, right? All of those features, we are getting those. And those are feature crosses. These are exactly things that we need. But then if we apply another layer, we will be getting even more crosses and then more and more. So if we have like 4 layers of this, we can have crosses for 4 features, up to 4 features. And this is very efficient. And one of the questions that might appear in your minds, it appeared in mine, why do we need that if we already have a deep neural network? Isn't deep neural network supposed to be able to approximate any kind of function if it's deep enough and has enough training data? So here, can it? Does it have enough training data? Well, yes and no. Theoretically, yes, but it will be what is called very simple and efficient. So it will take much more data to train a neural network to approximate all of these results. Why? Because neural networks by default are additive, right? Like we are adding different features, we are multiplying, passing through some non-linearity, and continue to add vectors on top of vectors on top of vectors. Here, we are explicitly multiplying. So we will be multiplying features time and again. And to approximate multiplication, neural network has to use many layers. And to train many layers, you need a lot of data, and it's basically inefficient. So it's much more efficient to separately train such a cross layer and separately train a deep layer and achieve the same result as we are trying to achieve in like this wide and deep architectures. So what's great about this, it has rich interaction modeling, deep crosses. Still the problem, yeah, it's hard to model sequential data. So what if now you want to do something like user interactions with previous n items or n movies or and whatever? How do you model it with this kind of an approach? You don't have a good solution. So there come some like transformers and other architectures, but maybe you can apply this as part of the deep part of this whole network. Um, and essentially, what I have read, from what I have read, this is still, I wouldn't call it state of the art, but the main idea, as you can see, it didn't change even from introduction of wide and deep. We are obviously continuing to improve that. We have introduced transformers. We are making this more complex, but it solves the core problem of high cardinality features very well by doing all of these feature crosses. And it's a very, very clever idea, if you ask me, about how to do feature crosses. Like this formula looks so simple, but the implications that it actually does all the possible feature crosses is definitely not obvious, at least to me. Okay, and that's it. That's everything that I wanted to tell you about high cardinality features. So let me stop sharing my screen and let me just tell you that I will see you next time when I will have a very, very short, short part where I will be discussing leakage and maybe, I don't remember, some other aspect of features. So that's it for today. Thanks for looking. If you have any suggestions about what I should talk about, feel free to leave comment, and I will see you in the next one. Bye.